Hello everybody. Today we shall look at application of what we have learned in quantum mechanics, in Schrodinger mechanics. So before we go any further, let me remind you what we are dealing with. So let me put these in points. First of all, we said that we will deal with only stationary states. Where the potential is only a function of x. It's not a function of time. And we said that the wave function in this case, and let me change my notation a little bit. Let me write this as capital psi, which is a function of x and t. This is just for convenience. It is difficult to write capital psi lot of time, and I will need to write this psi as a function of x from now on a lot of time. So just because of that, I just change. So I call the function, which is a function of x only, as psi, and the other one as capital psi. Okay, so stationary states, this has definite energy, and if I have states with definite energy, I should be able to write down the energy eigen functions, and these are energy. This is how the energy eigen function look like. So I have a definite energy sitting over there, and psi as a function of x is still unknown, and that comes from the solution of time independent Schrodinger equation. Time independent because this equation does not have any time in it. We wrote it in a few different forms, just juggling with different functions here and there, left side and right hand side. But essentially, if I give you a Vx and you know the conditions on psi, so that gives you boundary conditions on psi also, you will be able to solve for psi as a function of x. Once I know psi as a function of x, I put it back over here for a given energy. Remember, this will give you for that particular definite energy. So for that definite energy, you get the eigen function. So we also like to usually find normalized eigenfunctions. And that first will require that whatever psi we get, this psi x mod square dx is finite. If normalized, this is equals to 1. You see, one thing I did is I have not written e to the power I e t by h cross while I am integrating over psi. In general, I should do that. But here I know that if I put capital psi back over here and I do mod square of it, e to the I t by h cross and e to the minus I t by h cross will cancel each other. So I don't need to write that down explicitly here. Few things for you to remember. This cannot be 0 everywhere. Or infinite anywhere. Okay, so 0 everywhere. is continuous. These things we will use today, so that's why I wanted to write it down. We also said that we will deal with piecewise constant potential, which we discussed last time. It essentially means that in a given range of x, the potential does not change. So in a given range of x, so let's see what will happen. So this will become v0, and I can bring it to the right hand side. I can write e minus v0, and then I bring everything to the left hand side. This we did last time also, so I will not go through it again how to do it. So this is d2x dx2 plus 2m by h cross squared e minus v0. So Vx is V0 in this range times psi equals 0. And we looked at two cases for this. So one is E greater than V0. So let's call this thing as K1 square. The general solution in this case, so let me make a little space because we'll need it. The general solution in this case is psi So let me write it with psi1. It is just this denoting the case that it is the case E greater than V0. So psi1x is, so you see it's E greater than V0, so it's essentially oscillatory solution with K as the oscillation wave number. So A e to the I K1x plus B e to the minus I K2x. A and B are arbitrary, so that we will find out when we match the boundary condition. When we say that across, so this is only true for a given region. In the next region, the value of V can be something else. In that case, we will have to match the boundaries, the values of psi at the boundaries, and that will give us an idea about A and B. Sometimes we'll see that we'll know it up to a constant also. But this is the solution. You could have written it down in terms of sine and cosines also, but they are exactly the same thing. So whatever you write is fine. Similarly, for E less than V0, I can define now, I say let's call this K2. So I can define this as 2m by h cross square. I want K2 to be greater than 0, so I write V0 minus E, because V0 is now greater than E. So what will happen is, I will get this as minus K2 square psi here. So the solution now will be exponential instead of oscillatory. So let's call them with say C e to the now I K2x plus D e to the minus K2x. Okay, again C and D has to be determined from the boundary condition. Now this is what we did last time. So let us go to a particular case based on this. So in that case is the infinite square well. Okay, so this is just a name. So let me tell you what is the potential look. How does the potential looks like? So my x-axis is x, and this is my y-axis. And let me even not draw the y-axis because it will create some confusion shortly. Now let me draw. This is the place of y-axis. Draw a boundary here, and here I draw another boundary. As you can see, we said that potential is going to be piecewise constant. So this boundary is defined where the potentials are constant in between. So this is x equals to 0 and this is x equals to L. Now it is immaterial whether I call this x equals to 0. I could have called this x equals to 5 and this x equals to 5 plus L also, or x equals to minus L by 2 and x equals to plus L by 2 also. Because x-axis goes from minus infinity to plus infinity, obviously it is completely immaterial where we start the potential. Our solution may look different, the functions may look different, but the potential is this, that I have piecewise constant potential and I have three regions. In the region 1, so this is my region 1, here my potential is infinite. So is in region 3. See, it's an extreme case. Potential is infinite there as well. The potential in the region 2 is 0. So this is like, if you wish, you are being caged in between two very high walls, very high, infinitely high walls. So in classical case, you have no way you can go out of this wall, and inside the wall the potential is 0. So just let us consider that what it would have happened if I have two high walls. In classical case, just think about it, and then I have a ball in the uh, in the bottom. Then what will happen is the potential here you will not feel a 0 potential here. You will feel S potential there and a little bit more potential there. And if I now keep a classical particle, a ball over here, it will always try to come back here, stay there. But in the classical case, for this type of potential, now I have the bottom as flat. If I keep a ball over here, the potential is 0 everywhere in this region. So the ball can actually stay anywhere in this region. Now we are trying to ask the question, what will happen for a similar quantum case? So let me remove this figure. So it is just to make you understand things. So we are trying to get the counterpart of the problem, where we say what will happen to the wave function. So that is the first thing that we'll figure out, right? Now, what is the way to proceed? So first I write down wave function in three regions. So phi1. Now what will be phi1x? Phi1x, so let's see the region 1. So we have not defined what is the energy of the wave function. So first we have to define which energy for which I am trying to calculate the wave functions. So this is this energy, say. Okay. Now these type of states, so you can imagine that. Okay, let's proceed a little bit and then we will talk about it. So in case of phi1, so let's ask the question. So it's all right. So I have these three regions. So what is the value of k in these regions? Okay. So you see the energy is there E, and both of these regions 1 and 3 has a potential infinity. So if I still write it in terms of V0 first and say V0 tends to infinity, the energy is less than V0. So this is in this regime. So for this I can write K2 square equals 2m by h cross square. And you see V0 is very large, so let me just write V0 over here. Because V0 is very large, it's actually infinite. But for the time being, let's say it's very large compared to E. So I just write V0. So I'll not do any harm if I do that. Here also the K2 is same. I get the same K2 here because the condition here is exactly the same. In the region in between, which is between 0 to L, there the energy is some positive value and the potential is 0. which means that the energy is greater than V0. So I satisfy this condition. So there I have a thing like phi1, which is now 2m E minus V0, but V0 is 0. So 2m E by h cross square. Okay. So I have K2 here, and remember that the solution here is like e to the K2 type, and the solution here is e to the minus I K1 type. Okay, this just to remind you of how the solutions will look like in these three regions. And we'll explicitly write it down now. So region 1, the solution is, say, let's call it C. So let's call it C here. So any constant C. Now these are arbitrary constants. So if I multiply this constant with anything, that I can still call it C because it's arbitrary. But so anyway, so this is C to the K2x plus D e to the minus K2x. Okay, so let's see what happens to this constant C and D. Now remember that psi x has to be finite everywhere. Now let's say x is, so here in the region 1, so x is always negative. Say x is minus 100. Okay, so if x is minus 100, then what is d e to the power minus k2 times x? So this is this times 100. And you immediately see there is a problem, because since K2 is almost infinity, so this will make psi1x to go to infinity. If the only way we can save is setting d equals to 0. So if d is not equals to 0, psi1x will go to infinity. So which means that I have to set d equals to 0. So this term will go away. So I'll be left with C to the K2x. Alright. So let's say now what happens at x equals to x very close to 0. So it is like 0 minus, or we can say that x equals, say for example 0 minus 0.01. Okay. So if x equals minus 0.01, this term C e to the K2 times 0 minus 0.01 multiplication here. Remember, K2 is infinite. It's very, very large. How small you may make x, it will still be very, very large. So which means that I still get like C e to the power minus infinite, which is essentially 0. So the wave function in the region 1, so all this implies that d has to be 0, and if I put d equals to 0, the other term is essentially 0. So then psi1x equals 0. So this is between minus infinity to 0, x equals to minus infinity to 0. And the same fate you can see will happen to psi3x. So I request you to check that. So that will also has to be 0. So this is L2 plus infinity. So I request you to check this, but that will also be 0. So we have solved for the wave function in region 1 and 3. It is very trivial. It will be all 0. What is the solution in region 2? So let's write the solution in region 2 now. So let's call this psi2. So psi2x, as we said, it's exponential. So e to the I k1x. We call this k1, remember? So this is 2m e by h cross square. This is k1 square. So this should be k1 square. plus b e to the minus I k1x. And remember, these two tells you at x equals 0, it's continuous, psi is continuous, so this is equals to 0. X equals to L, also psi is continuous, so this is equals 0. Okay, so let's use these boundary conditions now. So first at x equals to 0, so what does it give me? It gives me a, so this is at x equals to 0. This term is 1, this term is also 1, so a plus b equals 0 implies b equals minus a. So immediately I can write now psi 2x. Remember, psi 2x is the psi between 0 and L. This equals, I take a outside, e to the I k1x minus, not plus, e to the minus I k1x. And that you will say is nothing but 2I times sine k1x, because this I can write as cos theta plus I sine theta, and this as cos theta minus I sine theta, and then that minus sign cancels the cos part and makes 2 of the sine parts. And this entire thing, as I said, that a is arbitrary, so you don't know what it is. So this entire thing I can write now as a. So this is a sine. So this is psi 2x now. It's a sine. And remember, what is k1? K1 square is 2me by h cross square. So this is root 2me by h cross square. That is k1 times x. Okay, so this is what I get at as psi x, just from one boundary condition at x equals to 0. Okay, so let us see what happens at x equals to L. At x equals to L, now this at L is 0, which is the fact that sine of, see, a cannot be 0, because if a is 0, then the wave function is 0 everywhere. Region 1 and 3 we have already seen it 0. If we make it 0 at region 2 also, that is not allowed. Wave function cannot be 0 everywhere. So that means that this part has to be 0. And sine of something is 0, you know that something has to be equals to n pi. So this implies that 2me by h cross square, square root of that, has to be n pi. Okay, so this, remember, this we called k1, so this I will also call kn, because obvious reason, but this is depend on n. Okay, now you see one thing important here, that this we said, remember that this has, we said, are the Eigen functions, right? So to start with, we said that for stationary states I can write the Eigen functions this way, this particular way. I can write the Eigen functions. We already know that given an energy, this will be the case. But now this is the function that you are solving for psi as a function of x. And then we said that we are dealing with the cases where we have piecewise constant potential. And in the classical counterpart of this potential, the particle will always be in between 0 and L, because there are infinite potential outside. So you see the psi outside, the psi at region 1 and 3 is 0. So all the psi which is non-zero is in the region 2, which also means that if I ask you what is the probability of finding the particle outside the region 0 and L, you will say definitely it is 0. So probability of finding the particle, so this we can argue here. So Px is non-zero in x equals to 0 to L only. Outside it is 0. So these states are called bound states because the particle finding probability of finding the particle is always within these regions. So these states are called bound states. So let's say bound states. First let me write down. So these are bound states. Okay. So the bound state happens when the energy, okay, so when the bound state happens, so we'll come back to in the next lecture because there we'll see something different than bound state. So then it will be more clearer. So let us just state the fact that these are called bound state for the time being. And so let me come back here. So this I called n. So this should I call En because for every n there will be one energy, and this n belongs to any integer. So this n can be 0 in this case at least, so plus minus 1, plus minus 2, etc. Fine. So or let me write En, which is the energy. So what will it be? So n square pi square h cross square by 2m. So these are the energies of the bound state. So these are the energy eigenvalues. And it so happens that these are discrete values. The energy cannot be anything. It can only come in square integer multiples. Square integer means n square, n is integer, of pi square h square by 2l. I forgot to write L over here because that is within sign. So I should have a L square here. Okay. Now let us look at what of these are possible energies. So possible values of n. So let us ask the question, is n equals to 0 allowed? Well, if I have n equals to 0, then for n equals to 0, what happens? I get 0 energy. Obviously, 0 energy is not possible. That we have seen from our idea of uncertainty principle, that 0 energy is not possible. There is a minimum amount of energy which is required. So n equals to L also makes k equals to 0. You see, n equals to L here will make k equals to 0. And k equals to 0 means if I put k equals to 0 here, again you get sine 0 for whatever x you want. So my phi2 also becomes 0. Phi1 in the region 1, phi1 is 0. In the region 3, phi3 is 0. Now phi2 is also 0. So which essentially means that everywhere the potential, the wave function is 0, that is not possible. So n equals to 0 is not possible, which means that n can belong to plus minus 1, plus minus 2, etc. Okay. So if that is the case, let us try to write down the solution for psi. So psi, this is now capital psi, which is a function of x and t. This is a e to the power minus I. Remember En t by h cross square. So let me write the En, or let us write En itself, because now these are discrete energies. So energy eigenvalues are discrete. And then I have sine of root over 2men by h cross square. But you see, this root over 2m en by h cross square has to be some n, and then we are writing everything in terms of n. So this I can write as n pi by L time x. Okay, so you may ask, how do I write this? Well, this is k and L. So this entire quantity has to be equals to n pi, and this quantity is also our k1, which now I am calling kn because it depends on n. So n pi is equals to knl. So kn I can replace by, so kn from here I can replace by n pi by l. So that's what I have done here, n pi by l times x. Okay, so still we are left with to figure out what is this a. Remember, this a is arbitrary. Now you see what happens if I have this sine n pi l by x. If n is positive, say n greater than 0 always, so which means I have two types of solution, because in originally n can be either positive or negative. So if I choose say m, or let's call it something else, so let's call it that we have a number which I called say what should I call, L. Okay, say L is a number which is greater than 0 integers, so L is like 1, 2, 3, etc. So if I consider all the possible values of n, so I can have sine L pi by Lx, and then other type of solutions which are sine of minus L pi by L times x, right? Because this will correspond to the positive values of n, this will correspond to the negative values of n. Now these I can always write as sine L by x sine times some phase factor I theta. This theta is a constant number. It essentially depends on what is the value of L. For a given L, it's a constant number. It's just that sign which is carried over in this constant number. Okay, depending on what is the value of L, if L is so depending on what is the value of L, I theta to the I theta will give you either positive sign or negative sign. Okay, so which means that these wave functions and these wave functions, one is for positive values of n and the other is for negative values of n, they just differ by a constant. So we said that we don't care about the constants because we already have a constant still to figure out, which is the amplitude of the wave function. So I don't need to consider the negative n values and the positive n values together. So which means I can say that we will only consider n greater than 0. Because even if we would have considered the n negative values, so that will just give me another value of a, another constant a. So we don't need to consider both of them because a is up to my normalization. So even if I consider the negative n values after the normalization, I will get the same wave function. All right. So the only thing to figure out is what is the normalization. So what do I mean by what is the normalization? Remember, I want psi x star psi x dx this to be 1, which now implies that both psi x and psi s star has this a square in it, and then I get this. So this equals to 1. So this is, if I can solve for a from this equation, then I am done. So basically what I have to do is I have to do this integral. Now doing this integral is rather straightforward, and because of that I will not do it here, but you can easily figure out that. So this is just doing a sine square theta integral. You know that sine square theta integral is always gives you. So remember that. Okay, so one thing which I forgot to mention, these integrals are minus infinity to plus infinity, but and then what psi I put it here is the psi at anywhere. So like this is true for only between 0 and L. Everywhere else psi is 0. So this integral from minus infinity to plus infinity, when I do this integral, I can break this integral from minus infinity to 0, but that integral will be 0 because psi is 0 there. Then 0 to L, so which is this integral, and then again L to infinity, again L to infinity integral is 0. So doing this integral from minus infinity to plus infinity, here I just need to do from 0 to L. And you will see that this integral value will come out to L by 2. This integral value will come out to L by 2, and A has to be taken as root over of 2 by L. Okay, so with all these, let me write down the solution. What I will request you is, before you look at the solution here, please go through the previous discussion once again and try to work it out yourself. So let me write down the solution here. Psi at x and t is, now I am writing the nth eigenstate, is root over of 2 by L e to the minus I en t by h cross sine of n pi by L times x. And you have this discrete energy eigenvalues, which is given by pi square h cross square by 2ml square times n square. You see several things here. If you make L larger, En reduces. So En is proportional to 1 by L square. En is also proportional to n square. So if I make n larger, then En increases. What if I make n very large? So let us calculate this difference delta E, which is E say n plus 1 minus En. Okay, see, this is telling you that there are discrete energy eigenvalues. If I consider these to be 1 for the time being, just in some unit, then the energy eigenvalues are 1, then n square is 2, and then n to the power n square is 2, then 9, then 16, etc. So I can, if I want to draw it here, so I have E1 here, which is 1 unit, then E2 here, which is 4 times E1, then I have E3 here, which is 9 times E1, E4, which is 16 times E1, etc., because it's proportional to n square. Now we are asking the question, what is the difference between the two consecutive energy levels. So for that it is straightforward. So this is 2m L square, and then I have to do n plus 1 whole square minus n square. That you know. So let's just concentrate on the n part. So this will be 2n plus 1. Right? So delta E goes as n. So or delta E goes as 2n. So if very large n, then this will go as 2n. So if n is very large, n very large, difference delta E goes as 2n. Okay, so let us ask the question that we have got this nice solution for the eigenstates, energy eigenstates. Remember that these are energy eigenstates, eigenstates of the energy operator. So I should be able to write down any wave function in terms of the energy eigenstates. So if I wish, if I have, this is an arbitrary wave function, psi xt, you know how to write it down in terms of the energy eigenstates. Which begs a question. So let's ask the question now. Is the energy eigenstate, which is this, is also a momentum eigenstate? Remember, we said that if two operators share the same eigenstates, then they will also commute with each other. You can do a measurement with one of the operator, and then do the measurement with the other operator, and both of these two measurements will give you commensurate results, such that you can reverse the order of operation between these two operators, and you will get back the same result again. So now let us try to see if this is also a momentum eigenstate. So I just operate these eigenstates of energy with P. Now P, if you remember, is minus I h cross del x. So I have to just use this on my wave function. Now this part of the wave function doesn't have any x dependence, it will just come out. So root 2 by L. So let me just still write it down. And then I have sine n pi x by L. Okay. So what will it give me? It will give me minus I h cross root 2 by L e to the minus I e n t by h cross. And sine x n pi x by L, if I do one derivative, I will get n pi by L. But then cos of n pi x by L. Remember that if it was a momentum eigenstate, then I should have got a sign here, because this I cannot now write as some numbers times psi n. To write that, I need psi n has sine, not cos. So to write that, I need to write it in terms of sine. So it's not a momentum eigenstate. Energy eigenstate are not momentum eigenstate. Okay. Now let us spend a little bit of time in looking at how these eigenstate look like. Remember that I forgot to write it here. This is true for x is less than L and greater than 0, and it is wave function is 0 otherwise. Right? So let us go back and see how these wave functions look like. So what I will do now is that I will show you how this thing look like psi n as a function of x and t. Sorry, psi n as a function of x. So only the x part, which is root 2 by L sine n pi x by L. And if I have the wave function psi all in n equals to n state, then how does the corresponding rho n look like? So rho n will be, so what I am claiming is that somehow I know that the wave function is in the nth energy eigenstate. Okay, so then rho n is just the square of psi n, so it will be just psi n star. It's already normalized, so it will be just this quantity. So look at these two for different values of n. Okay, so this shows psi and rho for different values of n, starting from n equals to 1 and then it goes up to n equals to 3. So let's look at the psi n for n equals to 1. You see, I have taken L equals to 1 only in this particular case. L is the width of the potential well, infinite potential well, and the boundaries of the potential well are given by these vertical dashed lines. The wave function you can see is 0 for x less than 0 and 0 for x greater than 0. That is true for all n equals to 1, 2 and 3 cases. For n equals to 1 case, you get a function which looks like this. It's a part of the sine curve. It is a sine curve between 0 to 1. If I look at the corresponding curve for the rho n, it is just a square of that, so it looks a little bit more sharper, because if I square it up, square this, it will become sharper. You can check that. Sharper means it rises faster. When I go to n equals to 2, so I get one more oscillations essentially. And when I square it up, so the oscillations, when I look at psi n for n equals to 2, there is a positive side and there is a negative side. But when you square it up, both of them become positive. So it's more like, again, an oscillatory curve between 0 and 1, but it has two maximas. So as you can imagine, for n equals to 1 state, the probability of finding the particle is maximum at 0.5. But for the n equals to 2 state, it is not at 0.5. It is at the places where the function is maximum. Similarly, you can look at the n equals to 3 now, which will have 3 such maximas. Okay, so we talked about where is the probability of finding the particle maximum, but we can also ask the question, what is the probability? So this is the case for n equals to 1 state only. What is the probability of finding the particle between say 0.5 and 0.75? What I have to do, remember, I have to integrate this curve. So this shaded region shows actually the area of the shaded region is the value of the probability, because what I do is I integrate rho n x from from that x ranges. And remember that the probability of finding the particle at a given region in space is same for all time, just because it's a stationary state. So that's the definition of the stationary state. So we can ask this question, what is the probability of finding a particle with energy. Now there cannot be any energy, so let's say the energy E1, which will corresponds to n equals to 1. In between, say in that example, it was half and 3/4. So what all I have to do is, so I will have to integrate between half and 3/4. This is the wave function, which is sine n is now 1 because we are talking about the one state, square of that. I will not do the integration because that is again not very difficult to do, but you have to figure out what is the value. Okay, so this is one type of question we can ask. The other question we can ask is that what is the expectation value of x? I'm writing in short form. So this means that what is the expectation value of x if the particle has an energy E1, which corresponds to n equals to 1. So now this is again given by minus infinity to plus infinity dx phi1 star x x phi1 x, and phi1 is 2 by L will come outside. You see the integration will become again 0 to L because that is the only region where phi is non-zero. And I can write this as x then sine square pi x by L. So I will leave all the integrations for you. I can ask what is this? Now this, if you remember, is square root of x square average minus x average square. So just I calculate x average here, so I have to calculate x square average also, putting a square on the x, and then I can write down what is delta x average. And just for fun, you can also calculate what is delta px. So this is the fourth exercise that you should do. So for this, if you calculate, say first delta px average, I will calculate that because you'll see that is very straightforward to do. So minus infinity to plus infinity dx 2 by L will come outside. There are 2 root 2 by L's that will give you 1 2 by L, and I have sine pi x by L, and all these I am doing for n equals to 1 state. So this is E1, this is also n equals to 1, this is also n equals to 1. You can do it for any other n states or combination of them. It's not a problem. So now I have, for the momentum operator, I have this, and which is operating on sine pi x by L. This will give me cos of pi x by L, and everything else is a constant. So this integration, when I do average of px, will boil down to an integration between 0 to L of sine of pi x by L and cos of pi x by L. Now, if you are familiar with integrations of sine and cosines, then you know that this integration is 0. Okay, I urge you to try this. So average value of the momentum is 0. And you can then calculate what is p square average. and find out what you get as delta px. Delta px, yes. Or let me write this as this. I should have not written. There's no average here, so this is delta x. And you can check the uncertainty relation. So these are the kind of questions we can ask with this wave function. Now just let me tell you one final thing. Here, as we saw, that the potential at the two ends of the wall at 0 and L is infinite. So the potential here is infinite. The potential here also becomes infinite in this entire region, which means essentially that the particle probability became 0 while finding the particle. Probability of finding the particle became 0 at the two ends. And we saw that boiled down to, say, if I look at the ground state, that boiled down to a ground state wave function which looks like this. Now this reminds us of something. There is a classical analog to this. The classical analog to this is the oscillation of a string which is fixed at the two ends. And the states we get here, the psi's, psi1, psi2, etc., are exactly equivalent to the strings. And in the case of string, we know that that is what we call a standing wave, which happens because there is one wave going this way and there is another wave going this way, and they are kind of adding up to each other. In our case also, we saw that we get sine n pi x by L as our wave function, which I can write as e to the I n pi x by L minus e to the minus I n pi x by L. Now, if you look at it carefully, each of these are actually eigen functions of also the momentum operator. This separately, not sine, but separately to the I n pi x by L is an eigen function of momentum operator. N pi by L is the momentum. It's related to the momentum. Here also, this is an eigen function of momentum operator. Here, the momentum is n pi by L, which is k times h cross. Here, the momentum is n pi by L times h cross with a minus sign. So this is as if there are two waves, which one is going in the right hand side, one is going in the left hand side, just like the classical analog. That's the last point that I wanted to make today. Thank you for your attention. I'll request you to go through the calculation and the logic by yourself once more. Thank you.